O- Okay, so in this video I'm going to talk about red-black trees. So red-black tree is a type of self-balancing binary search tree. A self-balancing binary search tree ensures that its height is order of log n after every insertion and deletion. Why do we need a binary search tree that is balanced? Because if we take a normal BST, then let's say we are inserting some elements in order of their increasing order. So every time we insert an element, the element will get inserted to the right of the parent, and thus all the elements will get inserted in one row. Now all of the operations like search, insertion and deletion will take order of n in that case. So that's why we need a self-balancing binary search tree, so that all of the operations are ensured to be kept within log n every time we perform insertion, deletion or a search. So let's see how a red-black tree helps us to keep a balanced binary search tree. Okay, so a red-black tree has the following properties. First, that the root, that first of all, every node has to be colored either red or black. Second of all, the root has to be colored black. Third, no red nodes should be linked together. There should be no edge between any two red nodes. That is, each red node has to have a black parent and has to have either null children or black children. And next, in a binary search, in a red-black tree, what we do is for each, we call all of these as the internal nodes, and we define an external leaf nodes on all of these nodes. So the leaf nodes are not colored, or they can be colored black, but they are not colored. We can take them to be not colored, and we place them below at the bottom of the red-black tree. So we can say that the black height of all the external leaf nodes has to be equal. So let's see by examples here, like which of these are red-black trees and how these, whether they satisfy the properties or not. So in the first one, the root is black. There are no red nodes, so obviously the second property can't be violated. And the black height of all the leaf nodes is 2, like 1, 2. So this is a red-black tree. Now this has a red root. Even though its leaf nodes have the same black height and no red nodes are adjacent, but it has a red root, so it is not a red-black tree. Now here we can see that this leaf node and this leaf node have different black depths. It has a black depth of 2 and a black depth of 1. By the way, the black height of black depth is the number of black nodes you encounter when you move from the root towards the leaf node. So while going from the root to this leaf node, I am encountering 2 black nodes, and going from here to here, I am encountering only 1 black node. Yeah. So as you can see, and in this red, so this is not a red-black tree. And in this, what we can see, this is also not a red-black tree, because while going from root to this external node, we have a black depth of 2, this plus this, and while going from the root to this, these leaf nodes, we have a black depth of 2. So the third property is satisfied. The first property is also satisfied, but the second is not satisfied because the 2 red nodes are adjacent to each other. This red node is child of this node. And finally, so this is not a red-black tree. And finally, when we move to this tree, so it satisfies all these properties. The root is black. The red nodes are not linked to each other. It has a black parent and black children. And also, if we look at all the leaf nodes, external leaf nodes, then all of them have the same black depth, 1, 2, all of them. So this is a red-black tree. So as we can see from these examples, the red-black trees are certainly more balanced than the trees which are not red-black. Like this tree has 1, 2, 3, 4, 5, 6 nodes, but it has a height of 4 again. But this can be rearranged to form a tree of height 3. Similarly for this tree. So we can see that red-black trees balance the tree using these properties. Now